I'm going to talk about my Sportsman GEN2000 generator, brushless type generator, and I'll be trying to investigate the peculiar, or some people call a trashy output of this generator. To do the investigation, I'll be using this little dual trace oscilloscope, which allows me to capture images and to download them to my computer so that I can print them out. So we'll be looking at a number of printouts that were produced by this oscilloscope. Well, first let's look at what we would expect in a good waveform. Let's take a look at just this image. If you would, please ignore the blue trace below. The yellow line is the output waveform coming out of my receptacle in my shop, and of course it appears nice and smooth, and it is a sinusoidal waveform, and at 60 cycles, 1/60 is 16.7 milliseconds, or 0.0167 seconds to complete one cycle. And by one cycle, let's say if this were the 0 point, from here to here would be one cycle. Well, I've got my dividers set here at about 16.1. And if I haven't moved this image around so much you can't see it, you can see it's a little wider than my dividers, but when we look at the generator output, they were actually running about between 61 and 62 cycles, so their cycle time is a little shorter than what I've shown. And again, this is plotted at 2 milliseconds for every major division. So what do we mean by 120 volt AC? Well, we're talking about an RMS voltage waveform, and what that means, 120 volts AC means that this voltage goes from 0 up to 170, back down to 0, and then in the negative direction, 170 volts. So if you take the peak voltage, divide by the square root of 2, mathematically that turns out to be the RMS voltage that we're working with. So let's take a look at some waveforms that were captured off of a couple of my generators. The top one that you see here is a Westinghouse generator, and it has a voltage regulator. And as you can see, the waveform is certainly not beautiful, but it's not bad. I believe that each of these little squiggles you see here is a result of the rotor as it passes over the slots in the stator. It causes a little disturbance, but it's a pretty good waveform basically, and this is being operated without any load on it. And when a load is put on, a lot of times these little blips will tend to disappear or certainly be reduced. The bottom one is my little Sportsman generator. And what is characteristic, first of all, we notice that the little blips are more exaggerated, but we have a real deviation like here and here and here on the leading waveform, and this seems to be characteristic of any brushless generator. And what I'm going to try to talk about today is why do we have this distortion. Okay, now let's take a look at the generators we're talking about. Just take a physical look at the generators. This unit is supposedly rated at about 1400 watts, although it pretty well seems to max out at about 1000. It's a typical Chinese clone unit. If we step around to the end of the unit, I've got the end plate off. We can kind of see what similarities and differences between it and in a generator with a automatic voltage regulator has. Basically, you see here there is no voltage regulator here. Over here we have a diode which produces takes DC off a winding and provides DC output for charging batteries and so forth. And then the other connection here, you see some additional wiring that I've done to this. Basically, there is a capacitor in the circuit. There, I think you can see it. It's located just on the back side, just surface mounted. A couple of wires come out. They go down and connect to a winding here. And this additional wiring that you see, I've connected into that capacitor circuit. The black wire is connected to one side of the capacitor, and the two blue wires are connected in series in that circuit with the capacitor. So basically, I can put an amp probe on one of these blue wires. I can measure the current coming through it with a clamp on, or by connecting, let's say here and here, I can get a look at the waveform of the voltage going into this capacitor. And if these two blue wires are connected together, then the capacitors in the circuit, if I remove one of the wires from this connector here, then it's opened up and the capacitor is cut out of the circuit. So I can kind of take a look and see how it acts with the capacitor in the circuit and without it. The second generator is a unit that has a voltage regulator built into it. It's a Westinghouse unit. It's rated for 120 volt output, supposedly 3600 watt rating. The best I've been able to do with this is about 3300 after changing out the carburetor and doing what I could to kind of it was running terribly lean when I first got the unit. The carburetor helped. This unit is different because here is the voltage regulator, which right at the moment is unplugged, and here is a connector going to that voltage regulator. To the wires, there is a red and white wire in this connector, which seems to go back. My own meter readings indicate this. It's connected to the output of the alternator here, which I guess basically tells the regulator what the output voltage is. And then two blue wires come off an independent winding off of the stator, and apparently that power coming off of that independent winding is used. It is rectified, converted into DC, and then comes out to these two wires to the brushes, which are located up in this area. Now the operation here seems pretty straightforward. Basically, you're taking a little power off of the output winding of the alternator. It's run through this regulator, which converts that AC into a DC signal. Then it regulates the amount of current going through these brushes into the rotor, and from that the rotor current is raised and lowered as needed to get the desired output voltage. Seems pretty reasonable, pretty direct. However, the brushless unit has a lot of mysteries that I'm hoping that we can kind of take a look at today. I created this sort of simplistic sketch that's intended to illustrate the major features of the brushless generator. And my pencil here is pointing at this shape here is the rotor, and the rotor has a winding on it, and the winding is shorted with a diode. And the stator, this outside portion here coming around, is intended to represent the stator. And we have 3 windings on the Sportsman. This winding has a capacitor shorted across it. This winding has a full wave bridge rectifier, and that produces 18 or 20 volts of DC output that can be used for charging a battery. And then this one that I've labeled with a VO would be the main power output winding. To give you a little more detail of how I believe this particular generator is wired, I prepared this sketch, and as best I can tell, we have 13 slots, then we have 2 empty slots and 13 more slots, and then 2 empty slots. And the ones that have the dot or the X in them represent slots that have windings in them. So we have 4 slots with nothing in it. And I'm going to make a statement here which I'll try to support with a little more detail, but just take it for granted, if you will, for a moment. I believe, let's say this rotor is going to turn clockwise in the image that you're looking at. I believe that the first slot has the winding in it for the capacitor, and its conductors will go in here, come up on the opposite side 180 degrees, then go back in. In other words, this would be loops of wire going through these 2 slots. And let me put my movable rotor in here just for discussion purposes. I believe that what happens as the rotor passes this slot, voltage builds up in these conductors. Now this is the conductors I'm talking about are the ones that are connected to the capacitor. And it builds up and it builds up and it builds up and it builds up, and as the tail edge of the rotor passes it, the voltage drops off, falls off. Then as the rotor continues to turn and it approaches this slot and this slot again, except now the voltage induced in the winding going to the capacitor is just reversed. And the other statement I'm going to make that I believe is supportable, but you may have some questions about that, is that every time this rotor passes this winding, it induces a current in this winding, and the diode is forward biased, so that we get a current flow and a bump up in the flux field in the rotor. And the interesting thing about this is that if we turn it 180 degrees, so now it's inducing again a reversed voltage in the winding that's going to the capacitor. Because the winding on the rotor is turning with the rotor, the diode is still forward biased. So every 180 degrees we get a bump, we get a current in this coil, which causes a bump up in the flux field, and it guarantees that we always one end of this rotor is north and the opposite end is obviously the south. So it becomes like a bar magnet rotating in this stator. Now I have a little bit of evidence here I'm going to try to present to support my opinions. And what you see here is a bitmap taken from my oscilloscope. And the yellow is the output voltage, and the blue is the voltage on the winding going to the capacitor. Now, in this case, the capacitor has been disconnected, so the output voltage of the generator will not build up, to 120 volts. In fact, it's only moving up about 17 or 18 volts, about 17 volts peak to peak, and then the winding to the capacitor is about 51 volts. Now these represent voltage waveforms. They are not current waveforms, they are voltage waveforms. So the generator is sitting there putting out kind of a voltage that's going peak to peak about 17 volts. And what is interesting about this is the voltage that's driving the capacitor, and I have made up a chart, just a scale if you will. Hopefully you can read the numbers on it. And these numbers represent milliseconds. Again, this is plotted at 2 milliseconds for the major divisions. So if you put this on here about like so, you see you get about 4.1 milliseconds for this voltage blip here. And the same thing happens in reverse here, and then it's repeated here. So every 180 degrees we get this voltage spike in reverse direction going to the capacitor, coming off of the stator winding that's connected to it. So if we take a look again at our sketch, what I'm claiming happens here is that, let's say the edge of my rotor is approaching this slot that has the winding in it for the coil going to the capacitor. As this turns, then the voltage begins to pick up very quickly. It continues to build. And then when this rotor reaches this position, then this voltage begins to collapse. Well, we know that there are 30 slots and that there are 360 degrees in the circle, so each slot represents about 12 degrees of movement, well, exactly 12 degrees movement of the rotor. And we know that it takes about 16.1 milliseconds for it to make that complete rotation. So if this rotor moves from here to where it collapses, and you count the number of slots, you have 8 slots. That works out to be about 4.3 milliseconds for the tip of this rotor to move from here to here. And again, going back to our original image here, taken with an oscilloscope, there's about, well, there's 4, there's 5, a little about 2 or 4.3, depends on where you're at, is the total width of this little pulse here. So that works out exactly. So that is my reasoning for saying that I believe that all the windings for the circuit, for the coil that drives the capacitor, is in this 2 slots. Now, if you further follow this approach further, now assuming that this rotor, let's assume the rotor tip is about here now, the voltage in the output windings are beginning to climb because this is the first coil in the output winding. And I believe there are 12 windings that are connected probably in series to make the output coil of this generator. So if you rotate this, the question then becomes, okay, if the voltage is starting to climb here, where is it going to go back to zero? And my argument is that, let's say this was rotating again clockwise, and we get to about here. Now we're beginning to get the ends of coils that are seeing the opposite magnetic field on it, and those are opposing these that are wound in the other direction. So this is going to force the output voltage to drive to zero. And if you count the number of slots from here to here, I came up with 16 slots, and that works out again using the same math as 8.6 milliseconds. So going back to our original plot from our oscilloscope, if the voltage starts climbing, I'm going to say it starts doing its thing about there. I'm beginning to see some wiggles as though the edge of the rotor is just approaching the slot. And here it goes back through the 0 point. Well, lo and behold, it's about 8.3, 8.4, and we estimated 8.6. So it all depends on how accurate you think this scale is, but it's just about right on. So the windings that produce this waveform, in my opinion, are distributed over the entire face of the stator core. And I don't think I said this before, but basically the way I'm looking at it is this is a two-pole generator. So this side represents one pole, and this side is the opposite pole. So this becomes my support for believing that first of all that the winding that drives the capacitor is in one slot, and then the output windings are distributed in the remainder of the slots around the perimeter. Now I did carry this one step further. I looked at the output voltage of my DC output, and again the DC output has a winding on it, and it has a full bridge rectifier. So what you see here is the 0 point is up here, and this has to do with the way I hooked the meter up, the polarity of it. But this becomes a pulsating DC output. The rectifier is changing the AC. So if we say this voltage is going negative, if we didn't have the rectifier in, this would be flopped over. So, and I've got my dividers here set on about 16.1 milliseconds of distance. So as you see, that's just exactly one cycle. So it appears that the winding that's used to produce the DC output is also distributed in these 12 slots. So actually these 12 slots have two windings in them. One is the main power winding, and the second one is the winding that's used to get the output that's used for the DC. And again, then we have one pair of slots, this one and its neighbor 180 degrees away, that are carrying the winding for the for the capacitor. Now I'd like to show you this plot. This again is my Westinghouse generator, or no, excuse me, my Sportsman generator. And you see the typical divot. It is producing approximately 120 volt AC in its own messy way. And the blue line is the capacitor has been reconnected, so the voltage has built up, and the blue line is the voltage across the capacitor. And again, this is quite a long ways from being a sinusoidal wave, so you know, we would expect that peak to be, if this were a perfect sine wave, to be from the 0 point up to the top to be around 170 volts, and it's up over 243 volts, but I think a lot of that's due to the rather ragged form. But what is interesting about this waveform that I want you to observe is that the voltage, this being the voltage waveform across the capacitor, and the capacitor again is in the circuit. It starts out at 0, builds up, and looks like it's 328 volts, so it's pretty high voltage. It gets up to here, and then suddenly it breaks and goes into oscillation here. And I'm going to call that oscillation a ringing of the circuit. Now, if you go back to my little graph here, and you start at the 0 point, and you go to the peak of this voltage right here, it's right there is about 4.1, 4.2 milliseconds. And if we go back to our graph where the capacitor was disconnected, the distance from here, including this little divot here, was about 4.2. So clearly, this is the little blip that's driving our voltage to our capacitor, first in one direction and then in the other. And when I say it's ringing, what I mean, this oscillation that I'm talking about here, when I say it's ringing, what I mean is, take a look at a circuit like this. Here we have an inductor, and in this case the inductor would be the coil winding for the capacitor on the stator, and this would be our capacitor. And just for this discussion, I'm going to call this a battery and say it's capable of 300 or 400 volts. And these are switches. If you close this switch, very quickly this capacitor is going to charge up to a voltage equal to what the battery has. If we open this back up, we still have this fully charged capacitor. Now, if we close this switch, what will happen is this capacitor will become like a battery or a power source in this circuit, and current will flow from here into the inductor, and so the capacitor is draining its energy into the magnetic field of the inductor. So the electrostatic field of the capacitor is being changed into a magnetic field energy. But as soon as this happens, then the inductor, once the current flows for a time in this direction, the current will try to flow again in the reverse direction, and you get a back and forth that is decaying. And the reason it's decaying is that the energy is being eaten up by the resistance in this winding. But it's like a bell. If you hit a bell, it rings and then decays. The same thing happens electrically, and the same thing seems to be happening in our circuit. Now, I went one step further with this and produced another image. This is a lower image, and in this case, now you notice the peak of output voltage of the generator appears to be much higher than it is here, but unfortunately the volts per division, the scope setting was different. This one's at 50 volts per major division vertically, and this is at 100. So these are the same two waveforms. They're just the sensitivity of the scope has been changed. And this blue line this time is a plot of the current coming out of the capacitor. And the way I obtained this was that I put about a 1.1 ohm resistor in series with the capacitor, then connected my scope across that resistor, so any voltage produced through the resistor is a result of current flowing through it. So this gives you a more dramatic indication of the change, and you can see here, first of all, when the capacitor begins to charge at this point and this point, it draws a very high current, but up in this area, then the capacitor begins to approach the voltage of the output of the driving waveform here, and so the current begins to fall off. And everything is fine until this driving voltage disappears. And the reason the driving voltage disappears is that the head or the edge of the rotor has passed the slot that contains the coil winding. And so that voltage that's driving this whole thing just disappears. And then the capacitor and the inductor, which is the winding on the stator, go into oscillation, and it oscillates, looks like a couple times, and then settles down, and then it repeats itself over again. So if we look, the basic waveform of this is established by the rotation of the rotor inside the stator. As the stator moves past the coils, more and more flux lines are cut, and this produces a voltage in the output coil. However, there is another way that voltage can be generated, and if something happens to internally change the flux in the rotor very quickly, then that will be reflected in the output of the generator, and that's what happens here. You see a very dramatic, very steep drop or change in the current level. That change in the current level equates to a change in the flux field of the rotor. And it goes down, it's driven down, the output voltage is driven down, and then as it oscillates back up, the current gets less and less, the voltage starts to recover, and in fact then the current actually flows in the negative direction, which helps drive the flux field in the correct direction to help drive this voltage on up. And then it falls again, but not nearly as, this is very steep, this is less steep, and we have another distortion waveform right in here that's a little more difficult to see as a result of this. When it settles down again, then this continues on. So what we're seeing here is that each time the rotor passes the winding coil that the capacitor is on, it gets a boost in flux, gives a boost in the flux in the rotor, but that magnetic field in the stator goes into oscillation when the driving voltage disappears. I'm sure the designers of this thing would have liked to have come up with a way to keep that from happening, but apparently it's not easy, or they would have done it a long time ago. So the real cause of this deviation in output voltage is the capacitor and its winding going into brief oscillation for a few milliseconds. I have located on the internet a 1981 patent that was issued here in the United States for the brushless generator. And in my notes that I attach with this video, I'll try to give a link to that if anyone wants to take a look at the patent that was issued with this. Now, I will warn you that the patent, of course, does not deal in any way with the distorted waveforms that this type of generator produce. They're primarily dealing with how they can operate this generator and have a relatively constant output with a slightly changing engine RPM and changing load, and still get a constant output voltage without having a voltage regulator on it. But if you want to follow through on that, you may find that of interest. Now, the assumptions I've expressed here are somewhat my opinion, and I could be in error on them. I would certainly welcome comments from anyone who might have more superior knowledge on this generator, but I haven't really found much reference that describes the inner workings of how a brushless generator really works. I also invite you to take a look at some videos that are produced by Mr. James Condon. Mr. Condon typically does repairs of all types of generators, including brushless types, and he occasionally will have an oscilloscope hooked up so you can see the output of the brushless type generator he's looking at, and I'll try to leave some specific links to the videos that deal with this. The result of my investigation is not quite what I expected. I really thought that this major distortion in the waveform was probably the result of the switching action of the diode on the rotor. But when I began to investigate, that opinion was not supported. Instead, it seems that this deviation is a result of the capacitor and the winding is connected to breaking into a brief oscillation or ringing action, and that's that's producing the strange, trashy looking output of this type of generator. I hope you found this video of some interest and perhaps of some use. Thanks for watching.